Hello, welcome. We are going to be talking today about finding the zeros of a function. In order to do this, one of the skills that's going to be needed throughout this lesson is factoring trinomials. So that would be any equation of the form f of x is equal to ax squared plus bx plus c. And so just a quick review of the way that I factor, if you have a different way of factoring that works for you, go for it. But just in case, I want you to be able to follow what I'm doing. The steps that we're going to take are to find two numbers that multiply to be the product of a times c. That is this first coefficient and the last coefficient. And we want those numbers to add to equal b, the middle coefficient. Then we're going to rewrite that middle term, bx, as the sum of two terms with the coefficients that we found in step one. Then we're going to factor the GCF from the first two terms and factor the GCF from the second two terms, and then we're going to factor the result. So I'm going to show you exactly how this works using this equation here. We are going to factor the trinomial negative 6x squared plus 19x minus 10. So the first step that we're going to do, just looking back up above, we're going to find two numbers that multiply to be the product of a times c and add to equal b. That means we need to find numbers that multiply to be negative 6 times negative 10, because that's A and negative 10 is C. And that's positive 60. And we want to find of those factors, we want them to add to be 19, because that's our middle term. So the first thing that I'm going to do is I'm going to think of numbers that multiply to be 60. So 60 is equal to 1 times 60, which is 61 if I add it. So that's too big. It's also 2 times 30. But if I add those, I get 32. It's also 3 times 20. But 3 plus 20 is 23. And it's 4 times 15. 4 plus 15 is 19. So that's okay. Although keep in mind that if I had wanted them to add to negative 19, I would have had to use negative 4 and negative 15, which would have still multiplied to be positive 60. That's not the case in this problem. It's just that be careful of your signs because they do matter. All right. So what I'm going to do now, the second step is that I'm going to rewrite my b of x term, my 19x, so that I get 19x is equal to the sum of two factors with 4 and 15 as coefficients. So 4x plus 15x. So when I rewrite my expression, I get negative 6x squared plus 4x plus 15x minus 10. Now I'm going to factor by grouping. When I say factor by grouping, what I mean is that I want to factor the first two terms and then the second two terms. And when I say factor, what I want to do is extract the largest divisor that would evenly divide each factor. So the factors that make up negative 6x squared are negative 1, a 2, a 3, xx. And the factors that make up 4x are 2 times 2 times x. So the greatest common factor here is going to be an x and a 2. That's the common factors that are in both of them. Notice that 4x has two 2's, but only one of those 2's is common. So I can only pull out a single 2. So I'm going to factor out 2x. And in order to figure out what goes in the parentheses, I just say, what would I multiply by 2x to get negative 6x squared? I would multiply 3x. And actually, I'm going to pull out a negative 2x here because it's always nice when your leading coefficient is positive. So my 3x should have a positive one, so a positive sign. So if I pull out a negative 2, I would have to multiply that by negative 2x, or I'm sorry, by negative 2. Here we are, in order to get 4x. So negative 2x times negative 2 is positive 4x, which is what I want. Now, when I'm thinking about how to factor 15x and 10, I have no common x's because 10 doesn't contain a factor of x, but 15 is going to be equal to 3 times 5 times x, and negative 10 is negative 1 times 2 times 5. Those are just my prime factors. The common factor here then is a 5. It's the only factor that's in both. So I'm going to pull out my 5. And I would multiply 5 by 3x in order to get 15x, and by 2 to get negative 10. I'm sorry, by negative 2 to get negative 10. So these are my two factored groups. But now the last step, well, the third step up here is to factor the resulting expression. And I should have a common term as long as I correctly completed steps 1 and 2, which I do. 3x minus 2 is in both terms, so that's what I'm going to factor out. So I get 3x minus 2 times each of the factors that have not been accounted for. So times negative 2x plus 5. So my factored expression overall, I get negative 6x squared plus 19x minus 10 is equivalent to 3x minus 2 times negative 2x plus 5. If I were to multiply these two terms out using FOIL or distributing twice, I should get the exact same thing that I started with, which is negative 6x squared plus 19x minus 10. And so I'm going to be using those steps in order to find the intercepts and the zeros of a variety of functions within today's lesson. So just another quick review, intercepts are the points where the graph of an equation intersects an axis. For the y-axis, the intercept is the point or points where x is equal to 0. We call it 0, b as the point. I can find the y-intercepts by substituting the value of 0 for x in the original equation and then solving for the y that gets. And there may be more than one. For the x-axis, the x-intercept is the point where y is equal to 0. We also call it a, 0. So in this little graph that I drew, we see that we have one intercept, which is 0, b, which is where the y-axis intersects the graph. And then we have a second, or I'm sorry, we also have x-intercepts, and there's two of them. At A1 is what I'm going to call it, and at A2, what we have are the points A1, 0 and A2, 0. So there are two x-intercepts on this graph. If we're working in particular with a function, then the x-intercepts of a graph are called the zeros of a function because they're found by finding all x values that make the function, for example, f of x, equal to 0. The maximum number of real zeros is the value of the degree of a function, and that means the largest exponent on the independent variable. I'm going to talk about that when we get to one of the examples down below, so if you're not quite sure what that means, don't worry, I will go over it when we're dealing with an actual example. There are several different ways to find the zeros of a function, and the one that will lead us to an exact algebraic solution is by evaluating f of x equals 0. These are the steps I'm going to take, and then I'm going to apply it to two different examples below. First, I'm going to replace f of x with 0, so that I get 0 equals my equation in x. Then I'm going to factor the GCF of the function for any polynomial function other than f of x equals mx plus b, which is a linear function. If it's a linear function, we don't need to factor it because it's already in, we already have a product of linear factors, and it is easy, well, much easier to find the zeros. So we'll look at an example like that in a moment. Then we're going to solve for all values of x that result when f of x is equal to 0. So what we want to do is figure out what x's I would plug into each factor in order to make my overall equation equal to 0. And then last but not least, we'll consider whether or not all zeros have been found by looking at a graph or by considering the degree of the equation, which is the highest exponent on x or on the independent variable. So here's an example. We're going to find the zeros of this first function. This first function is of the form f of x equals mx plus b, which means that this is a line. Now, it's a lot easier to find the zeros of a line because a line can only cross the x-axis one time unless it's a perfectly horizontal line. So all I need to do here is go up to my first step, which is to replace f of x with 0. That's going to give me 0 equals 2x minus 28. Now, because there's no exponent on the x, this makes it very easy to solve. All I have to do is add 28 to both sides of the equal sign, that is. These make a 0 pair, so I'm left with 0 plus 28 is equal to 28. And that's the same as 2x plus 0, which is just 2x. The last step to isolate for my variable is to divide both sides by 2. If I do that, 2 divides 2 one time, and 2 divides 28 14 times. So my final answer is that x equals 14. So when x is equal to 14 in the original equation, f of x is equal to 0. And we can check that by substituting 14 back into the original equation. F of 14 is equal to 2 times 14 minus 28. Well, that's just the same as 28 minus 28, which is definitely equal to 0. So our correct 0 for this function is x equals 14. And I said earlier that we could also check by confirming on a graph. So I'm going to go to the Desmos software now. You can use your graphing calculator to do this, but because I don't have access to that on my iPad, which is what I'm using to share these notes, it's easier for me to use Desmos for this case. I'm going to type in the equation y is equal to 2x minus 28. So that is my equation, and I'm going to zoom out here, and you can see here are my intercepts of the graph. I'm going to take a picture of this and insert it into our notes so that we can refer to it. And I can write on it that way too. And so I'm just going to put my graph in here. And what we see is that there are two places where this graph crosses the axes. It crosses the x-axis right here, which is at the point over 14, which we just found, right? Because f of 14 is 0. So over 14, comma 0, or we could write that as f of 14, excuse me. F of 14 is equal to 0. These two things mean the same. Our y-intercept over here is down at negative 28. When we're finding the zeros of a graph, we're not usually reporting the y-intercepts, but it's important to note that that is where we see that 0, okay? So this graph confirms that our 0 of the function is when x is 14 and y is equal to 0. So this visual inspection of the graph confirms our algebraic work. The next example that I'm going to do is a little bit more complicated. This is a polynomial equation, and the degree of this equation is 3. That's because the highest exponent on x is a 3, and that means that we can anticipate 3 roots. At the most we can have is 3. We may have fewer than 3, but we will not have more than 3. Okay, so to follow the steps that I wrote above, I've replicated them here so we don't have to scroll back up. The first thing that I'm going to do is I'm going to replace g of x with 0. So instead of g of x, I'm going to write 0, which gives me 0 equals x cubed minus 8x squared plus 16x. The next step, and this is what our general steps are, this is not a line, so our next step is to factor the greatest common factor of the function, because this is a polynomial function other than f of x equals mx plus b. So to factor the GCF, I want the largest term that evenly divides x cubed, negative 8x squared, and positive 16x. I can think of these if I write the prime expansion You don't have to write this step. This is just to help you visualize how I'm getting this GCF. X cubed is the same as x times x times x. Negative 8x squared is the same as negative 1 times 2 times 2 times 2, because that's the prime factorization of 8. If I do 2 times 2, I get 4, times another 2 is our 8, times x times x. And for 16x, another 2 times 8 gives me 16. So I just have 2 times 2 times 2 times 2. 2 to the power of 4 is 16 times x. So when I think of the largest factor that evenly divides all of these terms, the only term that's in all three of these is x. So that is my greatest common factor. So the first thing I'm going to do is factor out my greatest common factor. 0 is equal to x times whatever's left when I multiply or when I take out one of my x's. I get x squared here. That's these two, x times x. Here I get negative 8x, because that's the same as negative 1 times 2 times 2 times 2 times x is negative 8x. And here I'm just left with my 16. So my greatest common factor is x. That's been factored out. And the next step is to continue to factor f of x completely. So to factor completely, what I want to do is check inside my parentheses here and see if this trinomial can be factored. And it can. I know that because it's possible to find two numbers that multiply to be 1 times 16 or 16 and add to be negative x. And I'll show you how to do that right now. So what I want to do is take 0 equals x times x squared minus 8x plus 16. And I want to break down this trinomial term. So I'm going to find two numbers that multiply to be equal to 1 times 16, or just 16. I get 1 because my a here, this is a equals 1, b equals negative 8, and c equals 16. So they need to multiply to be a times c, which is 1 times 16. And they need to add to be equal to negative 8. That tells me that at least one of my factors here is going to be negative. So 16 is equal to 1 times 16, or negative 1 times negative 16. 1 plus 16 is 17. Negative 1 plus negative 16 is negative 17. Those are not our factors. Also, 2 times 8 is equal to 16, but 2 plus 8 is equal to 10. And if I try the negatives, it's just going to be negative 10. All right, 16 is also 4 times 4. 4 plus 4 is equal to 8. That's the right magnitude, but we need a negative sign, which means it's going to be negative 4 times negative 4. And indeed, negative 4 plus negative 4 is equal to negative 8. So this is the one we want to use. As I continue factoring, the next step is to rewrite this b of x term as two factors that each have the coefficients I found in this step here. So it's going to be negative 4 and negative 4. Negative 4x and negative 4x are my two coefficients that are going to replace my negative 8x. I bring down the rest. I have my x squared and my 16. And I keep my parentheses and I keep my original factor of x. Now I'm going to factor by grouping, and I'm going to group the first two terms and the last two terms of my trinomial, which is now a quadrinomial, but that's okay. So to factor out the greatest common factor of those, I get x times, let's see, the greatest common factor of x squared and negative 4x is just x. And I would multiply x times x to get x squared, and x times negative 4 to get negative 4x. Over here, remember I said that I want the coefficient of x to have a positive value. So I'm going to factor out a -4 as the greatest common factor. -4 times x is equal to -4x. And -4 times -4 is equal to +16. So the last step here is to factor out my common factor of x minus 4. And I get x times x minus 4 times what I didn't use, which is an x minus 4. So here I have 3 factors, which makes sense because I had a degree of 3, right? My original highest exponent was a 3. And that's going to let me know here that I could have up to 3 roots. And so I do have 3 factors. However, you're going to find we only have 2 roots in this because x minus 4 is a duplicate root, or it's called a, what is that called? It's called a double root. There we are. And so I now need to figure out all of the values for x that result in this entire equation equaling 0. So I can think that through. If I have x times x minus 4 times x minus 4, any one of these factors equaling to 0 will cause the entire expression to equal 0. So for example, if I just let x equal 0 here, then I get 0 times 0 minus 4, that's -4, times 0 minus 4, which is again -4. 0 times -4 times -4 is equal to 0. So that means one of our zeros is when x equals 0. Additionally, I might figure out what number I could put in for x that would make either of these terms equal to 0. And if I do 4 minus 4, I get 0. So I'm going to let x equal 4. If I do that, I get 4 times 4 minus 4 times 4 minus 4. Well, these are equal to 0. So this is the same as 4 times 0, which is equal to 0. So we also get x is equal to 4 as a 0. So my zeros are x equals 0 and 4. And I want to consider whether this is all of the zeros. So I have already considered the fact that my degree was equal to 3. So I could have up to 3 zeros. And here I've only found 2. So I want to double check by looking at a graph. So let's go back to Desmos. And I'm going to enter in that equation. My original equation was y equals, or f of x equals, x to the power of 3 plus, let's just double check and make sure I get it right here. So minus 8x squared plus 16x. So I'm going to back that up and say minus 8x squared plus 16x. Nope, I didn't quite get plus 16x. And so we see this graph here. All right, and I'm going to do a screen cap so that I can draw on this. See? Let me just share my screen one more time. I'm going to take a screen cap. There we go. I'm going to copy this and insert it into our notes. And we get here this lovely little graph. And we can see that, in fact, this graph just crosses the x-axis in two places. You can tell there's a double root when the graph exactly touches and then rebounds off of the x. And this happens when x equals 4, and it actually has a full intersection when x is equal to 0. So a visual inspection of the graph tells us that there's only two roots. So you can find the exact algebraic roots by using a process of factoring and solving for 0. All right, we replaced our function with 0. We factored our polynomial completely. That gives us this bad boy. And then we identified all of the places, all of the values for x that would make the right side of that equation equal to 0. And then we can also solve by visually inspecting on a graph. However, if you're using a graphing calculator, you can get a numeric result by following some simple steps that I've included here. So I don't have a graphing calculator emulator for my iPad, but what I'm going to do is tell you the keystrokes that you would take in order to use a TI-83 or a TI-84 in order to find the roots. So the first thing that you would do is press y equals. That's going to clear any prior equation, or you need to clear out any prior equations and type your equation. So I'm going to use an example down here of x to the power of 3 minus 6x minus 3x plus 5. And again, you get this by pressing y equals. If you're using a TI-83 or an older version of a TI-84, you're not going to have these pretty colors, but it's still going to look the same way, okay? Then you're going to go ahead and press zoom. When you press zoom, you're going to select zoom standard, and that'll give you a 10 by 10 viewing window. However, if you can't see the graph, you may need to play around with those zoom options to zoom out until you can see it. Just like when we did this Desmos, I needed to adjust the window in order to have my graph perfectly centered. You may not be able to see your solution immediately when you're graphing on the calculator. That's going to look like when you press zoom, you're going to get this menu here. You can just hit 6, or you can scroll down and select standard. You could also zoom fit or zoom out, and if you don't see the graph. You can see here, this is the zoom window that captures the graph for this particular function, x cubed minus 6x squared minus 3x plus 5. Next, we're going to use the calculate menu. You get the calculate menu by pressing the second button and then the calc button, which is the fourth function key on a TI-84 Plus. However, second calc is also above the trace button on a TI-83 or a TI-84 that's not a plus. And option 0 is calculate zeros. And when you do that, you're going to get a screen that looks like this. You have this little X trigger here, or this little crosshairs here for X. You're going to have to select a left bound and a right bound. So I'm going to make sure that my crosshairs here are on the left side of this root right here. And when you hit enter, you're going to get a little line like this. And you have to select another side that's to the other side of that root. So we do that. Let's see. We use the arrow keys to move to the left of one intersection and hit enter. And then we use the arrow keys to move to the right of that intersection and hit enter. And then you hit enter a third time to guarantee that you have bracketed out the points on either side of that particular intersection. So when you hit enter a third time, you get this last screen here. And it tells you that when y is equal to 0, this x value here is 1.08 or 1.078653. You're going to have to repeat this process to find the other zeros, but you can do that as many times as you need. And you can also just do a visual inspection if you've done the calculations by hand. You can do a visual inspection to make sure you got the correct zeros there. All right, so that sums up our notes on how to find the zeros of a function and should take you all the way through the variety of exercises that you're going to see today. Thank you for your time, and please always reach out to me during office hours or by email if you have any questions about what you've seen here. I've gone ahead and posted these notes on Canvas. Thank you, and I just hope you have a great time here.